Orthogonal complement. So consider a vector space V and its dimension is capital D. Okay, the number of basis vectors are D. Okay, then consider another subspace of U and we name it as U, and the dimension of U is M. Okay. So the orthogonal complement of U is denoted as U orthocomplement. Okay, so U is a subspace of V and its orthogonal complement is represented like U orthocomplement, and U orthocomplement is a D minus M dimensional subspace of V, and it contains all vectors in V that are orthogonal to every vector in U. Okay, that is, it will be here. Okay, this part will be orthogonal complement. That means when we take any vector here and we take any vector in this x and y should be orthogonal. Okay, so that is meant by the statement. So every vector in U should be should be orthogonal to every vector in this U complement. Okay. Then the only element that are common to both the subspace U and its orthogonal complement will be vector 0. Okay, that is the only component. Any vector x belongs to V can be uniquely decomposed into this linear combination of the base vectors of U and its complement. Okay. So it can be written like sigma m 1 to m lambda m vm plus sigma j equal to 1 to d minus m psi of j vj complement or orthogonal complement, and where lambda m and psi j are real numbers and b1 b2 etc bm are the basis of U. Okay, so the first part is the basis of U, and these are the lambda values are the coordinate values, and this is the basis of U. And the second part is its complement vector space U complement, and it is its corresponding coordinate value, and B complement is the base vectors of U complement. Okay. Then the orthogonal complement can also be used to describe a plane U or a 2D subspace in a 3D vector space. Okay. So we can say that a plane in the 3D plane, in 3D vector space can be considered as a subspace, or we can take it as an orthogonal complement. The vector W with the length is equal to 1, which is orthogonal to the plane U, is the basis vector of U orthocomplement. Okay, all vectors that are orthogonal to W must lie in the plane U. Okay, so that as per the definition it is the case, all the vectors in W in U orthocomplement should be orthogonal to any vector in U. So that is also applicable to the base vectors. The anti-vector W is called the normal vector of U. Normal because the length of W is 1. So that is a normal vector of U. So we can assume a 2D plane like this. So this is a plane. Okay, and these blue vectors are the vectors lying on this plane. Okay, and n, we take this vector red one, that is the vector n that is perpendicular to this plane, and it is perpendicular to all the vectors in n. Okay, all the vectors in this plane. Okay, so when you take any vector on this plane, all those vectors are perpendicular to n. Okay, so in other words we can say like all the vectors perpendicular to this n is lying on this plane. Okay, So this can be taken as U, and the remaining part in the 3D space can be taken as its complement, orthogonal complement. Okay, so this picture gives you another viewpoint like this. This is the same plane U, and the remaining part is U complement, orthogonal complement, and this is the normal. Okay, or the vector that is perpendicular to this. So all the vectors in this plane are perpendicular to this vector. Okay, so that is the complement, orthogonal complement of the vector spaces. Okay, thank you.